When the Artemis II launch got scrubbed, you probably saw the headlines, right? Hydrogen leak. But well, that's just the tip of the iceberg. So in this explainer, we're going to go way beyond the news reports. We're going to dig into the really complex engineering and honestly, the fascinating physics that really put a hold on humanity's return to the moon. Yeah, because this isn't about some simple leaky faucet. No way. This is about NASA grappling with the raw, untamed nature of the most powerful rocket ever built. A rocket that, by the way, has been sitting on the launch pad for 3 years. This story, it's really about the fundamental challenges of leaving Earth. Okay, so to really get a handle on what happened, let's do this. Let's zoom in on the exact piece of hardware that slammed the brakes on that countdown. So say hello to the Tail Service Mast Umbilical, or TSMU for short. I mean, look at this thing. It's a 33-foot tower that is, for all intents and purposes, the rocket's lifeline. It's what pumps thousands upon thousands of gallons of super chilled liquid hydrogen and oxygen into the core stage. Without this, the SLS rocket is just a very, very big and a very expensive statue. Now, where it all went wrong was this tiny little part called the quick disconnect. This is the exact spot where the fuel lines hook up to the rocket. And I want you to just try and imagine the engineering challenge here. You've got a seal that has to handle fuel at unbelievably cold temperatures and insane pressure, but then it also has to pop off cleanly, perfectly, in the blink of an eye at liftoff. It's a total engineering paradox, right? And here it is. This is the number that brought the whole show to a grinding halt. 16%. Sensors screamed that there was a 16% concentration of hydrogen in the air, right around that umbilical. Now you might think, what's the big deal? Well, hydrogen's explosive limit is actually 4%. But for a crewed mission, NASA's rules are way, way stricter. And that's because hydrogen burns with a flame that's almost completely invisible. At 16%, the risk of a hidden, totally catastrophic fire is just too high. You don't take that risk with people on top. The engineers, they had a pretty clever plan, though. They tried something called a warm and reseat. So what they did was, step 1, stop the fuel flow. Step 2, they just let the connection warm up a little bit, hoping the parts would expand and maybe, just maybe, create a tighter fit. Then they resumed fueling, and you know what? It almost worked. They got the tanks all the way to 100%. But then, right at the end, in the final 10-minute countdown when the pressure is at its absolute max, it failed again. And all of this really points to the real star of the show. And, let's be honest, the real troublemaker here. Liquid hydrogen. It's often called a diva fuel, and believe me, it has earned that reputation. It is, hands down, the most powerful rocket fuel we have. But it's also, by far, the most difficult and finicky thing to work with. So you're probably asking, why even bother with such a diva? Well, it all comes down to a trade-off. See, liquid hydrogen gives you the highest specific impulse, which is just a fancy rocket science way of saying you get the most bang for your buck, the most thrust for the least amount of fuel. But to get that incredible performance, you have to deal with its insane cryogenic temperature. We're talking minus 253 degrees Celsius, and the fact that it is literally the smallest molecule in the entire universe. Okay, so this small molecule problem is absolutely crucial. It creates 2 massive headaches for engineers. First, hydrogen is so impossibly tiny, it can literally sneak through the atomic structure of solid metal. Think about that. And second, when you flash freeze that connection down to minus 253 degrees, the metal parts and the Teflon seals, they shrink at different rates. And that creates these microscopic gaps that those tiny, sneaky hydrogen molecules are absolute experts at finding and escaping through.
But here's the kicker. As if trying to wrangle this diva fuel wasn't enough of a headache, the hydrogen leak, it wasn't even the only problem that day. Yeah, even if that umbilical had worked perfectly, other issues would have almost certainly scrubbed the launch anyway.
Just check this out. First, a valve on the Orion crew capsule's hatch, yeah, it wasn't holding pressure. Not good. Then there were audio dropouts in the ground comm system, creating a very real risk of a comm blackout during the final countdown. That is an absolute no-go for a mission with astronauts. And then, as if that wasn't enough, a rare Florida cold snap was actually messing with the lubrication on vital tracking cameras. It was just one thing after another. So, okay, with all these issues piling up, what's the plan? How does NASA get back on the horse? Let's take a look at the methodical, step-by-step path they're laying out to get Artemis II back on track. First things first, technicians are going to go out to pad 39B, and they're going to replace the entire quick disconnect assembly. They're not just patching it up, they're swapping out the whole thing. Then, and this part is absolutely key, they are going to conduct a second full wet dress rehearsal. That's a complete fueling test from start to finish to prove under real-world conditions that the new hardware works. In fact, the crew won't even go into quarantine until that test is passed with flying colors. And all of that brings us to the new timeline. So you had the test failure back on February 2nd. The plan now is to do that second mandatory test in late February. If, and only if that succeeds, the new target launch date is March 6th, 2026. So you can see this isn't just a guess. It's a schedule built entirely around a really meticulous repair and verification process. You know, when you step back and look at all this, it leads to a final, really crucial thought. The Artemis program, it's about so much more than just building a giant rocket. It's about mastering the incredibly difficult, unforgiving physics of deep space exploration. And maybe, just maybe, taming hydrogen, rocketry's most powerful and most problematic fuel, is the ultimate test. It's the final exam that stands between us and our journey back to the moon and eventually beyond.